The next little bit that we have in this case is going to be the idea of looking for squares and cubes and powers of 5. And it's actually a pretty quick test to see if something is actually a square, if you know what the factorization already looks like. So if I go back to that example of 12 that we started with, I know that 12 is not a perfect square. If I were to take the square root of this thing, it'd fire off some horrible decimal, and that it wouldn't give me a nice whole number. Whereas if you looked at the number of 25, we know that this thing is a perfect square because it's simply 5 squared. We can actually very quickly identify if something is a perfect square by looking at all of the exponents. So if I were to look at, let's say, the number 2 squared times 3 to the 4th, this thing will be a perfect square, and the way that I can see that is because all of those exponents are even. If I have even exponents, I can actually rip out the exponent of 2 that I want. So what I can see here is that this becomes 2 squared. The thing over here becomes 3 squared, squared, and then each of those having a square means that this looks like 2 times 3 squared, squared. So you can see that this is of the form something squared. In particular, what I have is that this number started off by being something like 324, and it ended up over here as being the number 18 squared. So that's exactly what that little proposition up above says, is that if you give me some number, I know that it's going to be a perfect square if all of the exponents are even. That is, they're all multiples of 2. This procedure actually generalizes, so if I were to look at, let's say, 2 cubed multiplied by 3 to the 6th, I know that both of those things are divisible by 3, which tells me that this number is actually going to be a perfect cube. So what I can see is I can see that this looks like 2 cubed multiplied by 3 squared cubed, and then I can pull out that cubed, giving me 2 times 3 squared again, but now it's got an exponent of 3. So in general, I know something is a kth power if and only if all of the exponents are multiples of k. So it becomes this very quick test to see, am I a perfect square? Well, all of our exponents even. If not, not a perfect square. So here I can see almost immediately that 12 is not a perfect square because the exponent on the 3 is in fact odd. What you can do with this is you can start to look at some pretty cute little number theory puzzles. So I've actually stolen this one. In this case, it's a nice little limerick that has some kind of fun going on in it as well, and it allows us to make use of this unique factorization property. So down below I have this little limerick, which is read as saying, there once was a young lady named Chris, who when asked her age answered this, 2/3 of its square is a cube I declare, now what was the age of this miss? So it's got this nice poetic structure to it. And at the end of the day, my goal is to answer how old this young lady was. So the way that I do it is I'm going to identify her age as being some a. I know a is an integer. I'm going to assume my age is a nice whole number. I'm not, recording months or days or anything like that, just purely years. How many years old am I? Since a happens to be an integer, and I'm going to assume that she's older than 1 in this case, I'm going to view that this thing is going to look like 2 to some a times 3 to some b to 5 to some c, and you kind of see where I'm going. I'm going to just record that giant prime factorization of that a. What I want to do next is I want to think about taking 2/3 of its square. So I'm going to take 2/3 multiplied by a squared. And I actually did that on the next slide, so let's go ahead and see what that actually looks like. So 2/3 of its square. So if I square something that looks like this, what's going to happen is that all of those exponents are going to be multiplied by 2. So if you want to think about it, I'm going to have 2 to the a times 3 to the b. If you were to square those, well, you're going to square each of those separately, and if you square an exponent, it becomes multiplication. So this becomes 2 to the 2a and 3 to the 2b. And if I continue that process, you end up with this big mess. And then I have a 2/3 out in front. So 2/3, if I bring the 2 in, what's going to happen is that it's going to attack that little piece. Namely, it's going to increase the number of 2's that I have. So the exponent on the 2 has to go up by a 1. Likewise, dividing by 3 is actually going to decrease the exponent on the 3 by 1. So that's where I get this little +1 and -1 occurring, and everything else was unaffected. So now that I know that 2/3 of this square is supposed to be a cube, I can then ask, okay, what value of a makes this some multiple of 3? What value of b makes this some other possible multiple of 3? And so on and so forth. So what you can see is that to get 2a plus 1 to equal, let's say, a 3k1, and to get 2b minus 1 to be equal to some 3k2, I have a couple choices for what a could be. The first one that jumps off the page is a could be a 1, because I know that 2 times 1 plus 1 makes a 3. So maybe we take the a value to be a 1. Next up, I'm going to look at what makes 2 times b1 minus 1 equal to some multiple of 3. So here I could think, well, does 0 work? No, that fires off -1. Does 1 work? 2 times 1 is 2, minus 1. Nope, that doesn't work. What about 2? You have 2 times 2, which is 4, minus 1. So 4 minus 1 makes a 3. So that does in fact work in this case. So I can actually take my b value to be a 2. And then for the rest of them, I can actually take the lazy option of seeing, okay, well, I'm supposed to have 2c equal to some multiple of 3. Well, if I just take c to be 0, I get 2 times 0, which is 0, which is 3 times 0 as well. So for the rest of the chain, I'm just going to take all of them to be 0. So if I stuff all of that back up into my original definition for age, I get a, which is 2 to the 1, multiplied by 3 squared, and then a whole bunch of 5 to the 0, 7 to the 0, 11 to the 0, so on and so forth, which simply becomes 2 to the 1 times 3 squared, which in this case we already saw is going to fire off something quite nice, which is the number of 18. So that's actually an initial answer to my little limerick. So if I said there was a young lady named Chris who, when asked her age, answered this: 2/3 of its square is a cube, I declare. Now what was the age of the miss? In this case, the answer is 18. That is, however, not the only answer. So if you go back to this little equation that we had, is we had some choices for what a could potentially be. So I know that 2 times a plus 1 is supposed to be some multiple of 3. So we knew that 2 times 1 plus 1 made 3. So what about 2 times 2 plus 1? Well, that's going to turn out to be a 5, because 2 times 2 is 4 plus 1. So what about 2 times 3 plus 1? Well, that makes a 7. What about 2 times 4 plus 1? That makes 9. So instead of having a equals 1, I could actually swap out a with being a 3, which in this case would change things down below, is that instead of having a 2 to the 1, I'd have a 2 cubed. Whoops, I shouldn't say 3. I meant to say 4. There we go. So 2 times 4 makes an 8 plus 1. So my exponent becomes a 4. Sorry about that. So then my final age for this young miss is going to be 2 to the 4th times 3 squared. But 2 to the 4th times 3 squared is going to fire off something like 144. And if we're supposed to be assuming that she's a young lady, we're probably going to take the answer of 18 and not the answer of 144. So in this case, let's go with that as our answer. Knowing that we could actually generate an infinite number of these things, we're going to take this smallest answer that I see first. So the smallest a that works, the smallest b that works, and the smallest d and e and so on and so forth becomes this little chain that we originally saw. So you can jump this back to just some classic number theory puzzles as well. So if I wanted to find some positive integer n that made n divided by 2 a square, n divided by 3 a cube, and n divided by 5 some power of 5, you run the exact same game. You initially identify n as being this large product of primes. If you take n divided by 2, it's going to decrease the a by 1. If you take the n divided by 3, it's going to decrease the b by a 1, keeping everything else fixed. And if you take n divided by 5, it's going to decrease the power of 5 by 1. So since this thing is supposed to be a square, and this thing is supposed to be a cube, and this thing is supposed to be a power of 5, I know what those exponents are supposed to look like. That is, I need to have a minus 1, b, and c. They're all supposed to be even. I'm supposed to have a, b minus 1, and c are all supposed to be multiples of 3. And finally, a, b, and c minus 1 are then going to be multiples of 5. So that's using this fact of if it's a square, all of the exponents are even. If it's a cube, all of the exponents are multiples of 3. And if it's a power of 5, all of the exponents are multiples of 5. So now you look at this question of what value of a is going to make a minus 1 2 times something, as well as making a equal to 3 times something, and finally a equals to 5 times something. So sit and think about that for a little bit. What choice of a would satisfy that equation? Hopefully you can see that a being, let's say, 15 would work, because 5 times 3 is for sure a multiple of 5. 3 times 5 is again a multiple of 3, and if I take 15 minus 1, I get an even number, that is 14, which is for sure a multiple of 2. So I could potentially take A to be 15. And then you run that process the exact same way on the B's and the C's to hopefully see that A can be 15, B can be a 10, and C can be a 6, which gives me this very special value of n. And you can in fact see that if you took this divided by 2, all of the exponents are even. If you took this thing divided by 3, all of the exponents are multiples of 3. And if you took this thing and divided it by 5, all of the exponents would then be multiples of 5. Because I'd be decreasing the 15 by 1, decreasing the 10 by 1, and finally decreasing that 6 by 1. So it's kind of a cute little puzzle that you can very fast or very efficiently fire off what the final answer is supposed to be.